wish you have a good time in this class or in every week, any lecture of this course, okay? But I hope I can do my best to bring up the positive energy for this class. And I have said it many, many times, but I really want to say it again and again. Learning in English is difficult, but it will pay off. It will pay off, okay? Because our school has conducted a study, okay? The focus of studies is to understand the achievement of our students after graduations and how their achievements correlate with their records when they were a student in our school, okay? And they discovered that good students with better grades better grades do not translate directly to better achievements in society, okay? When they are fighting, working hard for their career development, okay? So our school has studied many such correlations, okay? Achievement in the job market and performance in the school. The only meaningful correlation our school can find between your school performance and your future achievements is English. People have higher score in taking English courses, have better achievements when they go to job market. I'm telling you the truth, the very, very truth, okay? It's not a theoretical study, okay? It's a data science studies, it's statistics. It doesn't matter how these two things correlate to the other, okay? You can have different interpretations, but the truth remains. Speak better English correlate with better achievements in your future career. That is the reason why I said it again. Learning in English is difficult, but eventually, if I work hard enough, it will pay off, okay? All right, first series is potential value. The other possible application is noise analysis. We can use Fourier series to separate useful signal for unwanted frequency contents. Usually noise exists in the high frequency band, okay? So by removing those removing high harmonics components from our Fourier series representation, we can come up with a cleaner signal, okay? Now, again, let's go back to this Fourier acceleration example. Remember that this is amplitude spectrum, and this is phase spectrum of this spring mass damper system, okay? Now, remember that we only have one term here. We actually, let's assume this is not just a sinusoidal signal. It's just, for example, a signal of x of t, okay? And x of t can be anything. No matter what it is, I can always, it doesn't mean always, usually I can find its Fourier series representation. And since Fourier series representation are made up of sinusoidal signals, so I can use these results to help us understand the response of this system when it is subject to an arbitrary input. Why can I do that? Because the Fourier series decomposition is particularly powerful for linear systems. Why? because linear time invariant system treat each sinusoidal component independently. All right, I have an arbitrary x of t. I have then its Fourier series representation, which is made of a lot of sinusoidal components, and I treat each of those components independently. All right, and that is not a problem because no matter what omega is, I got it covered, right? From here and here. Remember, C is a function of omega. Eta is a function of omega. So with the frequency response of this system available, I pretty much cover every omega. All right? No matter what omega is, O can always come up with the corresponding C and eta. Okay? So by using Fourier series representations, and I use my linear time invariant system and to treat each of those sinusoidal components independently, and superposition allowed recombination of individual responses. All right, because linear system satisfy the property of superposition. So I can study the impact of each harmonic one term at a time. And those results can be recombined to give me the full results, okay? And that would be an excellent idea because sometimes, you know, under this excitation of an arbitrary signal, the system just responds very poorly, okay? It creates problems. You know there is something wrong with this external input, but you probably don't know which part of that external signal is wrong. So what you can do is you break it apart by using Fourier series, and then you excite the system one term at a time to discover, to identify which part of the frequency components create the problem that you don't want. All right? So this transformation, this transforms a potentially difficult time domain problem into simple frequency domain problem, okay? Now, I don't want to deal with multiplication here, but we will talk about frequency domain multiplication in studying a frequency domain analysis for systems. Now, let's go back to Fourier series. Let me give you some examples of the Fourier series representations. Here, I have a periodical signal, which is a square wave, and its mathematical definition is given here. Its value can be either k or minus k, and its period apparently is 2 pi. By using the equalities that I gave you, I can compute Fourier coefficients, an and bn, use the formulas I learned from the course of engineering mathematics. And here, I know that an has to be 0. Why? Because an is the weighting function of the sinusoid sine wave, right? And sine wave, its very nature of sine wave, it is what? A function. By contrast, cosine wave is a even function. Here, what we have apparently is a function, okay? So, but it apparently is a function, okay? And an, correspond to cosine, which is an even function, okay? So when you take an a function apart, every component, it will not have any even function components, all right? Because what we are reconstructing or what we are try to synthesize is an a function, okay? So even function has nothing to do with a function. Therefore, m being the Fourier coefficients of cosine, its value had to be 0, all right, for this R function. By contrast, I can determine Bn, which is this, and I can write it out. I can write out the Fourier series as this, based on this result. As you can see here, Bn for this particular example decreases with n, which means higher harmonics has smaller amplitudes, all right? And let's synthesize this Fourier series, which means let's add the Fourier series one term at a time. X1 means I only include the first term, which is this. And X2 means I include these two terms into my Fourier series representation. As you can see, X2 is more similar to the original square function than X1. Why? Because I use more terms, and that result in better approximation, right? And I can go one step further by using even more terms, let's say 3 terms, okay? And then I get even better approximation, all right? Now let's go back to the Fourier series. There is one issue about Fourier series. That is, here we have an equality here. Usually, equality means both sides of the equality should have identical values, all right? But that is not the case for Fourier series, okay? For Fourier series, there is one important property that we need to be aware of. That is the conditions for convergences, okay? Now, for a periodical signal like this, when n goes to infinities, we are pretty sure, actually we are positive the Fourier series representation will converge to the real value, the original value, to the value of the original periodical function. But at this point of discontinuity, that is not the case. Why? Because Fourier series cannot synthesize discontinuity. Why? Because when we inspect the representation of a Fourier series, it actually consists of infinite numbers of sine and cosine functions. And the only difference between them are their frequencies. And no matter how high the frequencies of those sine, cosine are, they are always continued functions of time. And no matter how many continuous function of times you combine, it cannot create or simulate or synthesis a discontinuity. That is just not the case, okay? But what will happen when Fourier series encounter discontinuity? Based on this theories, it tells us, let's say X is a point of discontinuity, okay? Then let's assume that there are only finite number of such discontinuities. Then at the point of discontinuity, the Fourier series will converge to this, okay, which is the average values of the neighboring points of the original signals, okay? Right neighbors, right nearest neighbor, left nearest neighbor, all right? Pure and simple, okay? All right, let's look at second example for Fourier series representation. Again, this is a periodical function, okay? We just saw, and this is mathematical expressions. And then again, by using the formulas we just solved, we see that Bn is this. Again, and I forgot to put An here. It doesn't matter. The important thing is that this is the resulting Fourier series for this periodical signal. All right. Again, as you can see, as n increases, An and Bn decreases. So as long as n is large enough, or as long as the frequencies is higher enough, their Fourier coefficients become negligible, okay, which means their contributions can be ignored with minimum distortion, okay, with minimum side effects, all right? That is the reason why high frequency components, as long as they are high enough, usually doesn't matter. It's not that high frequency components doesn't do anything to the system. It is that a signal, a typical signal, always typically has very weak high frequency components. All right. Now let's synthesize the original signal by using this Fourier series. That is, let's reconstruct this signal by including more and more terms into the Fourier series representation. Okay, this here S5 means here n goes from 1 to 5. All right, so we only include the first 5 terms in the Fourier series, and this is the result. If we go to x8, okay, we include now 3 more terms, then this is what it looks like. And we increase more terms, let's say 15 terms. This is what it will look like, all right? Now, this is another view, okay? This is simply only look one period. Here, we have several periods. But the trend is very clear. That is, you include more terms in your Fourier series representation, you can have better approximation, okay? But one thing requires our special attention. That is, in synthesizing, in reconstructing the original signal, you will see that we have a problem at the point of discontinuity, okay? Because continuity is something Fourier series cannot represent, all right? So at this point of discontinuity, you see that the rate of convergence or the approximation error is relatively large, all right? That requires our special attention, all right? Now, let's use this spring mass damper example again to help us understand the idea of frequency domain analysis for signals, all right? Now, here, let's assume the system is no longer subject to a simple sinusoid excitation, okay? Instead, we have RT as our external force, and the RT is simply a triangular wave, which is defined here, all right? It's at a period of 2 pi, all right? And its shape apparently is a triangle, all right? So again, by using the formulas for Fourier coefficients, I can determine RT, the Fourier series representation of RT, okay? So these coefficients, these terms are actually, let me put it this way, the general representation of these spectral components or frequency components is this, which means if you set the value n, you set the value n to be 1, you get this. All right? Actually, you get this. If you set n equal to 3, you will get this. All right? If you set n equal to 5, you will get this. All right? Now, so this is actually a general representation of the frequency components of RLT. So RLT is actually a signal made of many, many harmonics. Okay? All the harmonics have different amplitude, but the difference is that the frequency just go higher and higher and higher. Okay? But since we have a general representation for these harmonics, let's just use this general representation to find the result for these differential equations. And this is what we will get, okay? Which means that the result, the solution for this differential equation will look something like this, where AN is this, BN is here, all right? And DN is this, okay? I will not go through the mathematical detail of how to get AN, BN, and DN because it's just simple. I wouldn't say simple, it's just algebra, okay? So teaching algebra is, of course, not a goal of this course, but you know how do we get this result, okay? You know the working principle behind these results. The important thing is I take my input apart into many components, and then I get a general expression for those frequency components. So I can get a general results for the response of the system. And then what I can do next is to, since I'm dealing with a linear system, I can add the result of each components together to determine the final response of the spring mass damper system. Okay, that is the strength of Fourier series. You can take things apart and then find solution for each, and then recombine them to reconstruct your final overall result. Okay, all right. This technique can be applied to essentially any periodical signals. Okay, because we can have a Fourier series representation for any periodical signal as long as that signal have at the most finite number of discontinuities. All right, finite number of discontinuities. All right, this slide is the purpose of these slides is just help you to recall the property of superposition. All right, now this plus tell you the input and output of the system we just studied. Okay, the input is apparently this triangular periodical signal, and this is the corresponding output. Okay, just give you an idea. All right. Now remember that Fourier series representation is originally designed to handle periodical signals such as this. All right. Okay. Okay. All right. Okay. But if this is the case, then we have a serious problem because in its original design, Fourier series representation is only good for periodical signals. But in the real world, periodical signals rarely exist. most of signals that we study are non-periodic. And in that case, if Fourier series become useless, then what's the point of studying Fourier series in the first place? Okay, so we need to come up with strategy of how to apply Fourier series to non-periodical signal. All right, okay. The answer to that question is actually Fourier transform. Okay, and Fourier transform has everything to do with what we learned in the previous weeks. That is Laplace transform. All right, but before jumping into Fourier transforms, let me give you some idea about the background. Okay, let's say the purpose here is to find the frequency components of this signal, which is e to minus t over 2, right? Okay, now apparently this is a non-periodical signal, so I cannot develop its Fourier series representation. Okay, I cannot do that. Okay, so what I can do is let's not inspect. Let's not deal with the entire signal. Let's just take a segment of that signal, or take a window, snapshot of that signal. Let's say what I'm interested is not the entire signal, but the signal on the interval between 0 and pi. Okay, so how do you determine this interval? Okay, it really depends on your applications. We will call this interval so-called region of interest. I did not invent this term, region of interest. All right, let's say 0 pi, the time interval between 0 per pi is the interval of interest, or region of interest. I only care about the behavior of this signal in this interval. Does that make sense? In real-world application, of course it makes sense. Let's say I care about the stock market. Okay, how do I care about the stock market? It's not from 100 years ago to next 100 years. I care about the market for the, let's say, past 10 days and next 10 days, all right? Because from those 20 days, I probably will discover the trend of the stock market, and then I can design my investment strategy accordingly, because present time information are the most relevant information. Therefore, minus 10 days to the next 10 days is the time period of interest, or time interval of interest. Okay, so the first thing you need to do in dealing with a non-periodical signal is you first identify the region of interest or interval of interest in the time domain. In this particular case, it's the time interval from 0 to pi. And then you take this segment and then you repeat it again. So this representation become a periodical signal. All right? Okay. Once it is presented as a periodical signal, then I can derive its Fourier series representation. That is how we get the job done. Okay. One particular phenomenon that you need to pay special attention to, that is by doing such an operation, okay, by performing such a conversion, unavoidably, you will create discontinuities. All right? Okay, why do we have discontinuities here? Because at the boundaries of these segments, usually they don't have equal values, okay? That is the reason why this technique will always, typically will, I should put it this way, not always, okay? If we get lucky, we don't have discontinuity, but that will only occur when the boundary values of this segment has identical values, okay? But usually that is not the case, all right? Now, let's go back to the idea of Fourier series, okay? Fourier series is really about analysis, which means you have an object and you take it apart. By examining its components one at a time, you have a better understanding of the overall function of the object. And so from here to here is really a process of analysis. But if we reverse the direction from here to here is really a process of synthesis, all right? Okay, now let's look into another potential applications of Fourier synthesis, okay? Noise cancellation, okay? You probably have some, a pair of Bluetooth earphones, okay? Or several pairs. How many pairs do I have? 1, 2, 3, 1, 2, 3. I have at least 5 pairs of six, at least. Personally, I have 6 pairs of Bluetooth phone. My TV, 1 for my iPad, 2 for my mobile phones, and actually 3 for my mobile phones, okay? And the other is for reserve, okay? I don't know why I spend so much money on those earphones, okay? All right, so how does it work, okay? A Bluetooth phones always has a microphone. Why? Because we need to use microphone to detect incoming ambient sound. That is sound from the surrounding, all right? Okay, because it is those sounds we want to cancel out. And sound is detected and sent to noise cancellation circuit, okay? So what it will do is it will perform Fourier series analysis, okay? And to have a Fourier series representation of the surroundings ambient sound. And then we invert ANC wave, cancel ambient sounds. ANC represent noise cancellation. What does A represent? Automatic? Okay, automatic noise cancellation. All right, so how do we do that? Let's say this is the waveform, which is the waveform of the ambient sound, okay? And the first thing we do is by detecting it with a microphone and then sending the audio signal to the cancellation circuit. And the cancellation circuit will determine its Fourier series representation. And then it will put a minus sign here, all right, to invert the waveform. And then that waveform will be produced by the earphone. So the earphones actually produce 2 signals. One is the original audio signals. For example, the music that you are listening to, or the podcast that you are listening to. Okay. Nevertheless, in either cases, you are listening to audio signals. Okay. And another component of the signal produced by the earphone is actually the inverted ambient sound. So these 2 waveforms will cancel out the other. Okay, that is how noise cancellation works. Okay, of course, you don't have to perform perfect cancellation. Sometimes you have some additional degree of freedom. Let's say you want to cancel 90% of the noise because you still want to have some idea about what's going on surrounding you, okay? And sometimes, for example, you want to cancel everything but human voice, right? Because when somebody speaks to you, you hope you can know that, you can detect that. Otherwise, it will be very impolite. And then you can find the ambient correspond to the frequency band of human voice and put that part and leave out that part from cancellation. Okay, you can only do that, but you can do that because you use Fourier series representation. All right. So in this regard, Fourier series representation is not just a mathematical technique, okay, that's make our life miserable. No, no. It is actually a very important and practical tools and has many real world application values. Okay. Now let's go one step further. Okay. Originally, what we have is a trigonometry Fourier series. Okay. Now we want to simplify Fourier series representation by using another way to represent the Fourier series, that is compact Fourier series representation, okay? And that is where the physical meaning emerges, okay? With a compact Fourier series representation, a Fourier series can actually written like this, and we saw this slide before, okay? This is the original trigonometry Fourier series representation. For each of its frequency components, which can be written like this, we can convert it to such a representation, where Cn is simply this, right? And theta n is simply this. So if you know An and Bn, apparently you can determine Cn and theta n without any difficulty, all right? So this is the frequency of compact Fourier series representation for any arbitrary signal. And here, Cn really represents amplitude spectrum, and theta n represents phase spectrum, all right? Now, what is a signal spectrum anyway? The spectrum of the signal is the frequency content of the signal, all right? It's a frequency components of the signals, okay? Now, it is made up of many sinusoidal signals, okay? Now, in English, when we say sinusoidal signals, typically, with no additional remark, typically we are talking about a cosine wave, okay? In English, when you say sinusoidal signals, it does not relate directly to sine wave. Conversely, when we say sinusoidal signals in English, typically it refers to cosine wave, okay? Anyway, a sinusoidal signal actually are the building blocks of all signals, because a signal, as long as it's periodical, you can always take it apart into the summation of many sinusoidal signals. So sinusoidal signal is essentially the building block of all signals, okay? Now, for each of those sinusoidal signals, it actually is made of three parts. Or I should put it this way, it actually has three important parameters. The first, of course, is amplitude. The second is phase. Now, these are two sinusoidal signals with the same amplitude and identical frequency. The only difference is their phase. So what does phase mean? Is the phase really means how do you move around in the time domain? Do you want to go one step further to the right, one step further to the left, one step further to the future, or one step further to the past? It is up to the phase. So phase has everything to do with time delay. Okay, keep that in mind. All right. And the third parameter for sinusoidal signal, which is what we say the building block of a signal, is frequency. So three parameters: amplitude, phase, and frequency. All right. Now with compact Fourier series representation, C0 is equal to A0. Don't forget, A0 is what? A0 is the DC component of the signal. What is the DC component of the signal? It is the average value of the signal, okay? Now, and Cn, theta, n are also well defined, okay? The definitions are over given here, okay? And again, please remember, Cn is essentially amplitude spectrum. When we say spectrum, we mean frequency components, frequency contents in the frequency domain, okay? And this is the phase spectrums. So as n varies, we see how Cn varies with frequency, because for n equal to 1, it corresponds to the frequency of omega, which is the fundamental frequency. How do you determine the fundamental frequency? You have to know the period of that signal, all right? Okay, once you know the period of that signal, you determine the fundamental frequency by dividing 2 pi with the period of the signal, all right? Now, each coefficient Cn corresponds sinusoid at a frequency n omega 0, all right? The energy contribution per period of power of that frequency component is Cn squared, all right? Remember that, okay? That is the definition of a signal, okay? All right? Cn squared, that is the definition of signal. We will talk about that again in the future, but now just have an idea, okay? But again, let me emphasize, the definition of signal is not the same as physical energy, all right? Okay, when it comes to energy contribution, the definition of the signal energy is not the same as physical energy, because for physical energy, there are many physical laws that has to be satisfied. For example, conservation of energy, okay? But that is not the case for signal energy. All right, let's go back to this example. Here, originally, we have a non-periodical signal, and by choosing the region of interest to be 0 to pi, I convert it to a periodical signal. And then by using these Fourier coefficient formulas, I can determine DC components as well as n, bn, these two Fourier coefficients. And by knowing that Cn is actually the square root of n squared plus bn squared, I can come out with the representation of Cn. Again, as you can see, as n increases, or should I say as frequency increases, the amplitude of that frequency components of the energy or the contribution of that frequency components goes down, 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 okay? Now, we can plot them as a function of frequency or a function of n, okay? And this is what it looks like. As you can see, for most of the real-world signals, its energy is actually concentrated on the low frequency band. And it typically decreases as the amplitude spectrum, typically, but not always, typically decreases as the frequency increases, all right? Now, another way to look at first a signal the frequency domain analysis is that we can always examine a signal from a time domain and a frequency domain perspective. In a time domain perspective, we simply observe that signal, the morphology, the waveform of that signal, and to understand, to monitor how that signal changes with time. Okay, that's very easy to understand. But we can also study the problem from the frequency domain perspective. How do we do that? We synthesize this signal by using different frequency domain, by using sinusoidal components with different frequency. And we can do that because we have a tool that we call Fourier series. So it has been proven that this strategy is valid, and you can always do that. And then we can have a so-called spectrum or amplitude spectrum in this particular case. And from this amplitude spectrum, it will tell you that we have several sinusoidal components. Each component has different frequency. It is very easy to see that. And each component also have different amplitudes, right? This is for this. This is for this. And finally, this amplitude is for this highest frequency components, okay? And that is how we study a signal from a time domain perspective and a frequency from a frequency domain perspective. If we can study the signal from these two different views, the results of our study can complement each other, okay? All right. When it comes to amplitude spectrum, it is easy to understand its physical meaning. But what does phase spectrum really tell us? Okay, let's say originally I have a signal, ft equal to t. Apparently, it is not a periodic signal. But again, let me specify a region of interest from, let's say it is from -1 to +1. So I convert this originally non-periodic signal into a periodic signal. And then I can determine its frequency components, its Fourier series representation. And this is the first harmonic. This is the second harmonic. This is third harmonics. And each of them have different frequency, different amplitude, and different phases. Okay? But how do we, what is the role of phase? All right? As you can see here, we have a discontinuity here. And discontinuity is the place where signal value has a final jump. So it would actually have a very rapid change occur at this point. And as you can see, for all these three harmonics, this point of continuities all correspond to the zero crossing points of these three harmonics. Why? Because remember, these sinusoidal components are all cosines, all right? And it has its largest derivative at the zero crossing points because the derivative of cosine is sine, right? Okay, and when cosine is zero, the value of sine is either 1 or -1, okay? And the value of sine cannot be larger than 1 and cannot be smaller than -1. So somehow each component know how to align their waveform so that they can synthesize this final jump more effectively and more efficiently. So space spectrum has something to do shared information, which means two signals can have identical amplitude spectra, but completely different waveform shapes due to different phase relations. Okay, 12 o'clock. Okay, that's the end of today's lecture. Again, thank you everybody for your participation. I'm looking forward to see you next week.